So as we go on, this one doesn't ask us to do a proof. It just wants us to find the limit. And one thing they tell us is that when we have polynomials, we can find the limit by direct substitution. So replace x with 9. 9 times 9 is 81 minus 2, so we get 79. So that's our limit. We're not proving it, but even if we made a table and picked x values closer and closer to 9, we would get an answer closer and closer to 79. Same thing here. Even though this is not a polynomial, our function is not undefined at 2. We get an answer when we plug a 2 in. 2 plus 2 is 4. The square root of 4 is 2. So that's what we're approaching. If we pick values closer and closer to 2, we're going to get an answer that's closer and closer to 4. The exceptions to this is when the value we're approaching is a boundary value, meaning it's close to where we become undefined or where something ceases to exist. We're not dealing with that right now. We're dealing with polynomials or polynomials raised to powers. And there are some other examples as well. Even if we have a rational expression, if this particular number does not make this undefined, then we can find the limit by direct substitution. Replace x with 7, replace the other x with 7, so we get 6 times 7 on top. We get 7 plus 2, which is 9 on bottom, so we get 42 on top. The square root of 9 is 3. That reduces to, 14. So that's our limit. As x gets closer to 7, we get 14. So that's nicer than having to plug in lots and lots of values to find out what we're going towards. Later we'll talk about continuity and discontinuity, and we'll look at times where direct substitution doesn't really give us the limit. But many types of functions we can just plug in, and that's what we get. If our function, if when we plug our number in, we don't have a whole or we don't have an asymptote, then whatever we're approaching there, if there is a point here, then as we approach that from both sides, that y value is our limit. So that's what we've done on these last several. We've had functions that whatever x value we're approaching, whatever x value that we're approaching, either from the left or from the right, when we plug that value in, we get a point. It doesn't make it undefined. So as we're getting closer and closer to that in the x direction, then whatever that y value is, that's also our limit, because that's what we're going towards. We're going towards that particular y value. So on this one, if we substitute a pi in, we have a 9 out front, tangent of pi. If you don't know that off the top of your head, then you can take out your calculator and you can take tangent of pi, which is 0. 9 times 0 is 0, so that's our limit. Now what about this one? Now this one, if we directly substitute 4 in, we get 4 minus 4 on top, which is 0. 4 squared, well 4 squared is 16, minus 16, which is 0 on bottom, and that's indeterminate. Indeterminate. So what does that mean? So it is undefined, but often when things are indeterminate, the limit exists. We are going to be approaching something, but the question is, what are we approaching? So we could make a table. We could pick values closer and closer to 4. But in this section, instead of making a table, they want us to solve this algebraically. So this problem is found in 1.3. So how are we going to do that? Well, let's notice that this denominator factors. X minus 4, x plus 4. Also, let's note that for that function is undefined when x is 4 and when x is negative 4. That denominator was originally x squared minus 16. If we put a 4 in for x, we get 0 on bottom. If we put a negative 4 in for x, we get a 0 on bottom. So this particular function, I'm going to call it f of x. That has a domain of anything except those two numbers. Now notice that we have a common factor between top and bottom. So we can reduce that function. And when we reduce that function, we get this function. I'm going to call that one g of x. Now if we reduce, fractions that are reduced are equivalent to each other. If we compare 4 over 6 to 2 over 3, those look differently, but they're equivalent to each other, meaning they are of the same value. So if we reduce a function, these functions should be equivalent to each other. They should have the exact same value. The only difference is f of x is undefined at 4 and negative 4. G of x is only undefined at negative 4. Every other place, the functions have the same exact value. And we could test that. If we substituted, for example, 3 into the top function, we would get negative 1 on top, 9 minus 16, negative 7 on bottom, so 1, 7. If we substituted 3 into the bottom function, we would get 1 over 3 plus 4, which is 7. Same thing. And that's going to be true for any x that we plug in except the x's that are not in their domain. Let's just demonstrate by using one more point. If we plug in 7, or let's say 8. 8, that's a little bit big to do off the top of our head. So let's pick something smaller. Let's pick 6. We plug a 6 in. For f, 6 minus 4 is 2. 6 squared is 36 minus 16, which is 20. So that reduces to 1 over 10. Well, if we get 1 over 6 plus 4, so we get the same thing. So these two functions are equivalent. They are of equal value everywhere except where they're. Now, for negative 4, they are both undefined at negative 4. But notice the top function is also undefined at positive 4. Is the bottom function undefined at positive 4? Well, no. So if we want to find out what is the limit as x approaches 4 of x minus 4 over x squared minus 16, since they share the same values everywhere except where they're undefined, then we should be able to compare that to this function and take the limit there. So this is f, this is g. So g, if we directly substitute a 4 in, we get 1 over 4 plus 4, which is 1 over 8. So for this function, by direct substitution, if x gets close to 4, our function gets close to 1 over 8. This function is still undefined when x is 4, but if we were to compare x values really, really close to 4, like 3.9, 3.99, 3.999, then the answer to that would be approaching 1 over 8. G is referred to as an extension of f. G is an extension of f. It's a comparable function that differs at a single point. So let's see. If we graph these two, at -4, both functions are undefined, so we actually have a vertical asymptote there. Now, when x is 4, g is 1/8, so that's that, and we're here. When x is 0, we're at 1/4, so we're here. If we pick negative values like -3, we would be at 1. So this function is doing like this. If we continued going to the left side, we would be doing like this. So this green, that's the function of g. Notice x cannot be -4. We are undefined at -4. We are defined at 4. At 4, we have a y value of 1/8. The only difference between g and f is that f does not exist when x is 4. Every other place, g and f have the exact same values. We demonstrated earlier that for other places, when we substitute the same value into g and f, we get the same answers. So their graphs are going to be exactly the same. Their graphs are going to be exactly the same with the exception of, at that point, f at x equal 4 does not exist. So for the function f, there's not a point there. There's just a hole. Well, if there's a hole there, all these points around it seem to be pointing towards where that hole is. So g and f are approaching the same point. G and f are approaching the same point. G actually gets there. F, there's a gap there. With f, we've got a little bitty part of our graph missing where x is 4. With g, we don't have a gap. We include that. But with f, we don't. But limits, remember, a limit is what we're going towards. So whether there's a point there or not, both functions are going to the same location. Hence, they're both going to 1/8. So the whole point here is, if our function is indeterminate at the x value we're going towards, if we can find an equivalent function that is not indeterminate or not undefined at that point, they are going to have the same limit. They're going to go to the same value. Now, this doesn't go there. Let's cut that and move it over here. Let's do this one next. If we substitute a 2 in, we get 2 plus 7, that's 9. The square root of that is 3. So we get 0 on top and 0 on bottom. That's indeterminate. So on the last one we did, we demonstrated that if we get 0 over 0, then if we can find an equivalent function where we can plug a 2 in and get an answer, they are going to have the same limit. On the previous one, we were able to simply factor the denominator and reduce the fraction. Here we have to do something differently because we don't really have a good way of factoring this. So if we have one such that we have a square root in it and it's indeterminate, there's a little trick that we learned in algebra, and we didn't really use it that much. But it's for rationalizing denominators. And in the past, if we had a radical on bottom, for example, the square root of x plus 2, if we wanted to make this radical go away on bottom, if there are two terms, to make it go away, we would multiply top and bottom by the conjugate. And we'll see why in a minute. That's going to make the radical go away on bottom. We'll still have a radical on top, but that would get rid of the radical on bottom. We would actually end up with that. So we're going to use that trick to try to make this radical go away. So we're going to multiply the top by the radical x plus 7 plus 3, and the same thing on bottom. Now on bottom, I'm not going to distribute that. I'm going to leave it in factored form, meaning this factor times that factor. But on top, I am going to multiply it out and see what I get when I make my radical go away. So we have to distribute. We're going to do this radical times that radical. And anytime we multiply a radical times itself, anything times itself means we have that quantity squared. And if it's a square root squared, those cancel, leaving us what's underneath. So since these match, that means we have this radical squared, so we're going to get what's underneath. Then we're going to do that times 3, so we're going to end up with 3 of those square roots. We've got to distribute the minus 3, so we have minus 3 of those square roots, so those cancel, and then a minus 3 times a plus 3. In the bottom, we're going to leave factored. So on top, we have a plus 7 and a minus 9. 7 minus 9 makes a negative 2. So the top simplifies to x minus 2. And then we have an x minus 2 times that parenthesis. Now the good thing about this is that we have a common factor between top and bottom. That and that cancel. That's going to leave us a 1 on top, square root of x plus 7 plus 3 on bottom. So we made the radical go away on top, and look what went away on bottom, that x minus 2. That x minus 2 is what gave us the problem to begin with. X minus 2 has a root of 2, or a 0 of 2. 2 is what makes that 0, which makes our fraction undefined. It turns out that when we got rid of the radical on top, we also got rid of that x minus 2 factor, so this is no longer going to be 0 on bottom. The very piece that was 0 when x is 2 now is gone. So 2 plus 7, that's 9. So we have the square root of 9 plus 3. So 3 plus 3 is 6. So even though our original function is undefined when x is 2, we were able to do some algebra. We multiply top and bottom by the same thing, so all we're doing is multiplying by 1, so we're still equivalent. So this fraction is equivalent to the original one. The only difference is where we are undefined, our domain. So they are going to approach the same y value when x is 2. So this one approaches 1/6. Therefore, the limit to this one is going to be 1/6 when x approaches 2.